So in an assignment, you guys showed, or you were supposed to show, that if you had a propagator which started at, say, some position x1 at time t1, and it ended up at position xn at time tn, and if the particle, it's a free particle in 1 + 1 dimension, right? Then the propagator, you basically solve it by doing Fourier transform, and then the propagator has a very simple form where you have a prefactor, which is important because it depends on the time interval. And then there's an exponential part, which is im/2 xn/x1 squared divided by tn minus t1. Okay? So do you remember this result from your assignment?
Assignment, is it like assignment 3?
No, I think it was assignment 2, right? Or 1?
It was the first one. Yeah, I
Yeah,
do.
the
Oh, yeah.
first assignment.
Right.
Yeah. So now we want to calculate that using the path integral. So if I write out the path integral for the free particle, what is the Lagrangian? The Lagrangian is just half mx dot squared, right? There is no potential energy. So the Feynman path integral in configuration space is going to be xn tn x1 t1 is equal to, we take the limit, n goes to infinity, right? We are dividing out the time interval to in n-1 equal bits. And because of n-1 equal bits, each will contribute a factor, which comes from, I think, the momentum integral that we had to do to come from the phase space to the configuration space. So this is delta t is the small time interval, and it has to the power n-1 over 2. Okay? So this is the prefactor, the normalization factor, and then we have an infinite number of integral dx n-1 dot 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 dx 2, right? And then in the exponential, we have the action, but the action is now divided up into small bits. So the integral over the Lagrangian becomes a sum over the small time intervals, I by h bar, and the sum goes from 2 to n-1, and inside the sum there is a delta t, and then which becomes an integral with respect to dt, and here m xn minus xn minus 1 whole squared divided by 2 delta t squared bracket ends bracket ends. Okay, so is this clear why this is the expression?
Will the sum go up to n upper limit?
Let's see, because what happened, how did we do this? We basically took the path, the time, we started at t equals to 1, right? And we ended at tn. So this was, say, t2. and then this was, say, T3, and this was, I don't think so, but let me check, okay? Because, okay, so what's happening is we have, okay, so we have this propagator which goes from here to here. And we are divided it into small propagators, one propagator that goes from here to here, another one that goes to here to here, to here to here, here to here, right? So you're right, Nahi, it should go to N. Yeah, because this is actually, yeah. Yeah, you're right, okay? So, because each of these guys come from the contribution of the propagator, right? So this is basically what we call, this measure, which involves this thing, and there's this thing in the limit where n goes to infinity. This is what we are calling x1 to xn, big D, x of t. So this is the definition of this, measure, this infinite dimensional integral. And in the limit where n goes to infinity, the sum, the Riemann sum inside the argument, in the argument of the exponential becomes an integral, right? So this becomes, so okay, so yeah, then this should go from T1 up to Tn. And then inside, this will become dt, and this is a classical Lagrangian, which is a function of x and x dot, okay? So let us now do the path integral for the particle which is free, okay? Any questions?
No, sir.
Okay, so we'll basically just have to do Gaussian integral. So the integral that we will need is simply the integral from minus infinity to plus infinity, e to the power minus a x squared, and a can be complex, plus plus of b of x dx, and this is done. This integral is done by completing the square, and if you complete the square, you generate a new term in the exponential, which is e to the power b squared by 4a, and then you use the usual complex Gaussian integral result to write the square root of pi over a. So in this expression, we have a lot of stuff which are constant. So we have delta t, we have m here, we have h bar here, stuff like that. So for now, and for now, delta t is being kept constant, right? Delta t is just a small time interval. So we can absorb all of this into a new variable just to make life easier. And the new variable is yn. Let's call it yn. And yn is defined by square root of m. What?
Yes, sir.
Okay. So our new variable is yn at m by 2h bar delta t in a square root times xn. So you saw all of this in the tutorial yesterday if you were there. So now if I express my path integral in this new variable, I get xn tn x1 t1 the usual constant, which is m divided by 2 pi I delta t h bar to the power n minus 1 over 2. And then we have n minus 2 y integrals, right? We have dy n minus 1 dot 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 dy2. So each of these will contribute a new factor, the inverse of this. And so we are going to get another factor here. So this times 2 h bar delta t over m to the power n minus 2 divided by 2. And the integrand now becomes e to the power I.
Sir, won't it be n minus 1 by 2 because we have n minus 1 variables here?
No, we have n minus 2 variables, right? Because this goes
No, from
to
y2 to yn minus 1 is n minus 1 variables. Oh no, it's not.
No, I don't think so. Right? I mean, এখানে যদি আমরা 1 থেকে শুরু করতাম, এখানে n minus 1 পর্যন্ত যেতাম.
Oh, yes, sir.
Right? So we have to be n minus 2. Yeah, no worries. I mean, এইসব নিয়ে আমার খুব problem হয়. So it's good to see other people are. Okay. So this goes from n goes from 2 until n, right? And this would be yn minus yn minus 1 whole squared. Okay, so now we have to do n minus 2 integrals. That's it. There is no magic here. So let's do the first y2 integral.